welcome to another Rockpile Tutors Homework Helper. Today we'll be doing some pre-calc homework from my local towns, Canton Plymouth High School. And what we're going to be working on is graphs of the non-sine or cosine trig functions. What's that mean? We're going to be looking at the functions tangent, which is sine over cosine, cotangent, which is cosine over sine, secant, which is 1 over cosine, and cosecant, which is 1 over sine. All right, let's get to work. For this video, we are going to be looking at the problems on page 311 of the textbook. And no, I will not be doing all of the odds from 1 to 45. I'm going to do a couple of problems from each of the sections, and we're going to generally talk about what I see from the functions. So let's start by talking about each of the functions. So if I look at the tangent function, right, I know that's sine over cosine. And what I want to do is I want to look at my unit circle and talk about what the tangent function does. So I'm going to shrink this down and bring it with me over to the unit circle. So if I'm going to look at the tangent function, what I've got is inside of the unit circle, for any angle, right, the x value is going to be my cosine, the y is going to be my sine. Right? And so if I think about the tangent at 0, where the sine is 0, cosine is 0, right, tangent of x is going to be 0. So tangent of 0 is 0. The tangent of 45 degrees, where sine and cosine are both square root of 2, that's going to be pi over 4, or 45 degrees, is 1. Right? And then as I get closer to pi over 2, I end up having tangent is 1, right? As I get close to 90 degrees, or to pi over 2, sine goes to 1, and the cosine is going to be a very small number. And this then is going to go to positive infinity. And because I can never get there, it's going to be an asymptote, a vertical asymptote, every pi over 2. So here it's going to head toward positive infinity. Down here I have cosine of 0 and sine of negative 1. So that's going to go to negative infinity. And it's going to repeat after I come past the vertical asymptote at pi over 2. As soon as I get into quadrant 2, all of a sudden I'm still at infinity because cosine is very small, but now it's a negative very small. So after I've reached this positive infinity, then as soon as I go into quadrant 2, then I'm going to bounce down to a negative infinity because cosine becomes a negative very small number and sine stays about 1. So each time this repeats, it starts at negative infinity, comes up through 0 at pi and 0, and then goes to positive infinity. Moving to cotangent, we see that cotangent is similar, but it is cosine over sine. And so its asymptotes are where sine is 0. Sine is 0, if I remember my unit circle. Sine is 0 at 0 and at pi. So now that's when sine gets very small as you get close, and I get a vertical asymptote there, and then a vertical asymptote at pi. And it crosses 0 at pi over 2, because that's when cosine is 0, and 0 over 1 right there is going to be 0. So those are the functions of tangent and cotangent. If I take a look at secant and cosecant, they look very similar. They're just in different locations. And this is because, which one is this? Secant is 1 over the cosine. And I know that cosine starts at 1, goes down to 0, down to negative 1, back to 0, and then up to 1. Look at the cosine, and we take the inverse of it. When cosine is 1, then the inverse of that is 1, and they meet at 0 and at 2 pi. At cosine equals 0, which is pi over 2, that's when I'm dividing by 0. And again, similar to the other one, if I look at my unit circle, as I get close to where cosine is 0, I go from a very small number, which goes to positive infinity. Then as soon as I get over here, I'm at a negative infinity because cosine is negative and very small. And then I repeat it again, centered around where cosine is negative 1, which is at pi. And so this repeating goes from just past pi over 2, where the inverse of cosine is negative infinity. It's going to come up to negative 1 when cosine is negative 1, and then do the same. And then it'll start all over as cosine gets closer to 3 pi over 2. And that's where, as it goes to 0, we're going to have positive infinity when the two signs are the same. And then just past, right? So as I get down here, 1 over the cosine is going to be a negative infinity, and then switch to a positive infinity and come back down to 1. And that is why we have this behavior here. All right? Cosecant is going to be the same thing except for sine, and so the function of sine is going to give me, starts at 0, comes up to 1 at pi over 2, back to 0, and then at negative 1 at 3 pi over 2, and then back to 0 at 2 pi. So for the same thing, we're going to have our vertical asymptotes where the function is 0. We're going to have 1 where the function is 1, and we're going to transition the same. And as soon as we switch from the sign being positive to negative, but close to 0, we go from positive infinity and then start over at negative infinity. And that's why that behavior looks like that. All right, so the next thing we're going to do is we're going to take a look at the actual sections of the homework. So what we have here is we have some vocabulary, and you should be able to answer these based on what we've done already. And then they want us to find x-intercepts, y-intercepts, intervals for increasing, intervals it's decreasing, relative extrema, and vertical asymptotes. So we can do that for all of them. I'm going to focus on cotangent, and I assume that you'll be able to do this for all of the other ones. So what I want to do is I want to look at the graph of cotangent and figure out all that stuff. So cotangent, let's find a good spot for this. All right. So cotangent, and again, this is not going to be precise, this is more about the concepts. And so cotangent follows cosine over sine, right? So it is going to be 0, and let's go with pi over 2, pi, 3 pi over 2, and 2 pi, okay? We know that cosine goes from 1 down, back, and here, and sine is from 0 up to 1, down to negative 1, and back to 0. So we're going to find the zeros of our function of cotangent. The zeros are going to be when cosine equals 0. So cosine equals 0 at pi over 2 and at 3 pi over 2. All right. When does it blow up? When are our asymptotes going to get there? That's going to be when sine is 0. So for sine equals 0, that's going to be at 0. So I'm going to have a vertical asymptote here. And at pi. And then also at 2 pi. Okay, so now what's going to happen as we get close? So as I get close to 0, if I'm a little bit above 0, let me get my unit circle again. There it is. So if I am close to 0, right, then my sign, if I'm just a little bit above 0, my sign is going to be positive but very small, and cosine is close to 1, which means I'm going to be at positive infinity. So, yeah, so my cotangent function is going to have a vertical asymptote heading up that way. We know that at pi over 4, right, which is where sine and cosine are both root 2 over 2, that's when I'm going to have my 1 because they're equal. And similarly, at 3 pi over 4 in the second quadrant, I'm going to be at -1. Right, so 1 and -1. And what my cotangent is going to do is it's going to go through there, go through the 0 I established, down to here, and then as I get close to pi, then again, my cosine is going to be negative, and my sine is going to be a positive, very small number, and that's what's going to take me down to negative infinity. I'm going to go out here and continue down here. Okay, and then for the second half, again, as I just get just past pi, now my cosine, right, so if I'm just past here, cosine is still negative, but now pi is a negative small number. And that's why I'm going to be at positive infinity just on the other side of that asymptote. And I'm going to come down and I'm going to do the same thing, going through 1 at the pi over 4, through 0, -1 at the next pi over 4, and down toward negative infinity. And that is, so what's that going to answer? What are my different questions? So that should help you be able to find the vertical asymptotes. So x-intercepts, that's going to be where it is 0. And in the cotangent case, it is where cosine equals 0. So that's going to be at pi over 2, negative pi over 2. Y-intercepts of the graph, in this case there are none because it's a vertical asymptote at y equals 0. Find the intervals when it is increasing, all right, and when it is decreasing. So let's take a look at that. So is this function ever increasing? It's not, right? It's always decreasing and goes through that. And so my increasing is increasing nowhere. It's decreasing from 0 to pi, both soft because it doesn't equal those. And then it is 0 and then from pi to 2 pi. Right? And any of these digits can be repeated every 2 pi. So it's going to be pi plus n 2 pi will give me all the repeating ones. So every 2 pi it'll be in this phase, and then this is 2 pi plus n 2 pi similarly. And so that's our increasing and decreasing functions. And then we're supposed to find relative extrema. And in this case, there are none because it's a continuously decreasing function. There's nowhere that it changes locally, whereas sine and cosine definitely have all of the local minima and maxima as you get to 1 and to -1 respectively. So that is how we are going to go through each of these 4 functions, identifying the vertical asymptotes, the zeros, the behaviors, and generating how we get there. I'll leave these 3 for you guys if you can. So now we'll also use these as the parent functions. The next is going to be transformations of the parent function. So let's take a look at that. So here I have 1/2 of tan x. So I'm going to start with my parent function. Right? Pi over 2, pi, 3 pi over 2, 2 pi. I know I've got my, for tangent, my asymptotes are where cosine is 0, which is pi over 2, and 3 pi over 2. And so if I were to draw my parent function, I would get this right here, right? That the first one comes from positive infinity, goes through 1, 1, 0, pi over 4, 1, negative pi over 4, negative 1, and then down to negative infinity at negative pi over 2. Okay, and then that's going to repeat here. And so what is the impact of this vertical shrink of 1/2? Really very little changes here, except that every point is 1/2 of it. So the extrema or the asymptotes don't really matter. And here, instead of being at 1, it will be at 1/2. So whereas the first one went like this, and this was at 0 and 1 and negative 1, now we're going to go a little bit flatter because that point is at 1/2 and negative 1/2. So the end behavior is the same, but in the 0 region, it's going to be a little flatter going from pi over 4 to negative pi over 4. And that's it. All right, let's take a look at the next one. 2 tangent of 2x. Now what we've got here is we've got a transformation that's going to do two things. So y equals 2 tan of 2x. All right, so this is going to do, my a term is going to do the same thing of taking that 1 in the tangent, right, where it's here, and I have 0, 1, negative 1, and that's going to make that 2. So that's going to make it a little steeper, negative 2. A little steeper through 0, but the same asymptotes, everything the same. Now, for 2x, what that's going to do is that's going to compress my graph, because whereas normally tangent of x cycles through from 0 to 2 pi, now I'm going to do the same thing between 0 and pi. So everything's going to get cut in half. And so what that looks like is, instead of being at pi over 2, pi, 3 pi over 2, and 2 pi, now I'm going to go in pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4, and everything's going to be just cut in half. So now at pi over 4, that's where my asymptotes are. And so now it's still going to go up to 2, so it's still pretty vertical. But I'm going to come, and in half of the width, I'm going to do that same thing. So this is going to end up looking like a squished version of the parent function tangent graph. All right, and so everything else, you either play with the a term and you scale the factors that have values. Usually it's the 1s, right? In this case, for the secant and cosecant, this whole thing will move up, because where it's normally 1, it's going to move up to 2, or down if you're shrunk. And then doing something to the x inside of the function, that affects the width, and it either widens it or shrinks it. Okay, let's take a look at what we have to do next. Let's take a look at one of the secant functions. What we're going to do is we're going to take a look at number 18, y equals 1 1/4 secant x. So 1/4 secant of x. Now let's think about what secant does first. Secant is 1 over cosine, so it's going to be 1 where cosine is 1, which is at 0, and then it'll go up to at pi over 2 where cosine is 0. We're going to have that vertical asymptote, and as cosine gets very small and positive, this is going to go to positive infinity, and then as I go down, or negative from 0, I'm going to go up to positive infinity again, because cosine gets very close to 0, but on the positive side. And then it repeats where cosine at pi, cosine is -1. I'm going to go down here, and then similarly from this vertical asymptote, right, I'm going to come up, I'm going to match it there, and then I'm going to go back down at 3 pi over 2, and then going out to 2 pi. I'm getting back to this point, so I'm going to repeat the left side of that curve coming down to 1 at 2 pi. Now, this is at 1 for the parent function of secant x, and all we're going to do is we're going to drop that down to 1/4 and -1/4. And so if we were drawing at the same scale, if this was 1, now I'm going to essentially come down to here. Yeah, so the secant of x, where it's 1, it's going to be 1/4 of that. So all of this is still going to be roughly the same. I'm just going to dive down a lot further. Similarly, this is going to be, I'm sorry, this is, if that's 1, this is 1/4. And if this is 1, -1, then this is -1/4. And I'm going to do the same thing, right? Follow my same end behavior near the asymptotes, but the point where it comes is going to be different. Okay, and we'll do one more like this, and let's hit one of the cosecants. So if I take a look at, how about number 26? Y equals cosecant of 2x minus pi. Where's an open spot? There we go. So what we're going to do is we're going to do the cosecant of 2x minus pi. All right, so this is a little more difficult. So let's focus on what the sine is going to do at 2x minus pi. So I'm going to start, as I often do, with the parent function. Parent function of pi starts at 0. At pi over 2, it's going to be 1. At pi, it's 0. 3 pi over 2, it's -1. And 2 pi is back to 0. So I'm going to go, let's call that 1, -1, and I'm going to go roughly like that. Okay, so that is my parent function. So black is y equals sine of x. And now let me do my two transformations separately. So here, first I'm going to do y equals sine of 2x, and that means that as it goes here, by the time it gets to pi over 2, I'm actually going to be taking the sine of pi. So it's going to do all of this stuff in half the time. So it's going to come up to 1 and back to 0 and then back to here and back to here. So that is just doubling it. It cuts the period in half. Instead of 2 pi, it does it in pi. And now let's go ahead and let's do equals, let's just look at sine of x minus pi. Okay, what that's going to do is that's going to take everything and shift it so that at pi, right, pi minus pi would be 0. I'm essentially starting it here instead of here. But after and so for the full period, right, if I don't have this 2x, then that means instead of being at 0 going up, now instead here at pi, I'm at 0 going up. So this is basically going to be the same as the inverse of pi, because at pi it's 0, and at 0 it's negative pi, right, which is also going to be going down. So that's going to start from here and go like that. And so now if I take the x minus pi and I do both of them to the point where I have y equals sine of 2x minus pi, now I'm going to do the same thing, and let's do that one in green. So because I've also shrunk the period to pi, moving it by pi basically means I do nothing different. So 2x minus pi is going to be the same as sine of 2x. And that's what our graph is going to look like. The green graph here of y equals sine of 2x minus pi. So I've got a shift to the left, and I've got a shrinking of the period by a half. I'm sure some of you are out there recognizing that I'm doing all of this work on sine, but the question is cosecant. So why am I doing that? I'm doing that because I'm more comfortable and I'm used to playing with sine, and once I do this, the cosecant is just going to be 1 over that. So let me draw that a little clearer as to what we're doing. And again, I'm going to start with the transformed parent function. So I'm going to start with sine of 2x minus pi. And like we said, that's going to go pi over 4, pi over 2, 3 pi over 4, and pi. And by cutting it in half, I now know I'm going to go up to 1, down to 0, down to -1, and back up to 1. And so my cosecant is going to be the inverse of this. And so where sine is 0, that's where my vertical asymptotes are going to be. Right? And then the inverse is going to be 1 at 1, and it's going to go to positive infinity around the 1. On the other side of pi over 2, we're going to invert at the -1, and we're going to be coming from negative infinity up and around again. Okay. Now, according to the instructions, I think you're supposed to do this for multiple periods and stuff like that, but I will leave the details to you guys to figure out what the actual homework should look like. That's how to attack transformations. The only one we didn't cover is where we have a +2 or something like that at the end, and that takes the function of the k, which moves the entire graph up or down. So whatever you're oriented around, whether it be the inverts at 1 in the secant and cosecant, or the transition through 0 for the cotangent and tangent, you're just going to move those points up and down, and everything else is going to move. Hopefully that was enough for you to get through the rest of the transformations. Now let's look at comparing the trigonometric graphs. We're going to look at, for instance, cosecant, and then we're going to look at sine of the same. And so we use Desmos, and this is where you guys could tutor me, because I'm sure you're better at it than I am. But the 2 tells us that our inverses are going to be here. And if I now add 2 sine of 3x, you can see what I've got, right? So my sine is in green, and where it's normally 1, 2 sine is going to be 2, and that's where the inverse is going to go. My vertical asymptotes are going to be accelerated by so essentially the period will be multiplied by 1/3, because every point I'm multiplying by 3, and that's why it doesn't quite hit, right? Normally the 0 is at pi, here it's at pi over 3. 2 pi is where the second 0 for sine is, and that's 2 pi over 3. And so this is what it's going to look like. And what are we supposed to answer here? Describe and compare the graphs. I'm going to leave that up to you. The key is where they are here, the inverse is where they're going to touch. The next section we'll be working on is problems 35 through 40. So we're going to look at it graphically and figure out where things are. We'll also look at it algebraically. So I'm going to do cotangent of x equals negative square root of 3. I'm going to start with my unit circle. And I know when I have square root of 3's and things like that, actually let's move that out of the way. Let's get that, let's find some space. Where's some space? There we go. So my cotangent, or my, I'm looking at cotangent of x equals negative square root 3. So I know that at my pi over 6, right, that's where I've got cosine pi over 6 is square root of 3 over 2, and sine of pi over 6 is 1/2. And so if I look at cotangent, which is cosine over sine, I'm going to have square root of 3 over 2 times the reciprocal of 1/2, which is 2, and that gives me the square root of 3. So here, where the cosines and the sine are the same sign, my cotangent is going to be that positive root 3. So for it to be negative, I want to go to the 2 quadrants where the sine and the cosine will be opposite signs, because then dividing them will give me a negative number. So that brings me to quadrant 2, where sine is positive and cosine is negative, and that's going to be 1/6 away from pi, so it's going to be 5 pi over 6. And then down here, let's pretend that's that same pi over 6. This is negative pi over 6, or almost to 12, 11 pi over 6, because 12 pi over 6 is 2 pi. So these are my expectations where the cotangent of x is equal to negative pi over 3. All right, so what we have here is we expect it to be at 5 pi over 6 and 11 pi over 6. And if I look, here's the 5 pi over 6 and 11 pi over 6. So that example shows you how you can go either algebraically or graphically to figure out, in this case, cotangent of x. So the rest of these you should be able to use between Desmos and your algebra. Hopefully you'll be able to do that. And so let's go ahead and, let's go ahead and take a look at number 37. Let's do one more. So the secant of x equals negative 2. So let's take a look at what that means. So my secant of x is 1 over the cosine of x. And I want to know where that is. What was the number again? 2 or negative 2? Help me out here, people. Negative 2 equals negative 2. So what I'm going to do, if 1 over the cosine is negative 2, I think pretty well in terms of cosine where that is. So I'm going to invert both of these. And I'm going to say cosine of x is at negative 1/2. Now you could do the inverse cosine of negative 1/2 and let the calculator talk to you, but we don't like to do that. Let's figure it out ourselves. So I'm going to go back to my unit circle. Anyone know where I put it? I know it's around here somewhere. There it is. Let me clean that up a little bit. Always keep your unit circles clean, people. All right, and what I'm going to look for is if the secant is 2, then like we said, the cosine is a half. And I know that up at the 2 pi over 6, or pi over 3, but I usually count in sixes, that's where the sine is the big one of the pair. So at 2 pi over 6, the point is cosine is 1/2, sine is root 3 over 2. And so I want it to be -2, so I've got to go to the 2 spots where the cosine is -1/2. Now that is going to be the same reflected over the y-axis, or 4 pi over 6. And then 90 degrees from that, sorry, more than 90 degrees, the opposite side where it's this one, which is going to be 2 more, so 6 pi over 6, 7 pi over 6, 8 pi over 6. Those should be my 2 answers, because that's where the cosine is -1/2, and that will make the secant be -2. So let's pop that in here. What did I want? I want secant of x equals -2. Okay, and if I zoom in, I'm going to have 2 pi over 3, which is 4 pi over 6, and 4 pi over 3, which is 8 pi over 6. People who've worked with me before know that I count in sixths because it's easier for me to figure out which of the pair, root 3 over 2.5, is each one if I go up in sixths. So yeah, if you like thirds, then it's 2 pi over 3, 4 pi over 3, but either way, it's good for you. The last section we're going to do is talking about even and odd functions. So let's take a look at the graphing and talk in general about what an even and an odd function is. We're mostly talking about the squared functions, or the even numbered functions. So if I look at y equals x squared, whoops, and I learn how to spell equals, right? I know what that's going to look like, right? That's a quadratic. And if I look at y equals x, which is an odd function because it has an odd exponent, I notice that as my end behaviors, right, my end behaviors are going to be x approaches, or y approaches infinity as x approaches infinity, and y approaches -infinity as x approaches -infinity. And you'll notice that for odd functions, the end behaviors go in different direction. One goes positive, one goes negative. For even functions, right, they go in the same direction. So x squared, for instance, both end behaviors are in the positive direction. If I were to make this a -x squared, now both of my end behaviors are still in the same direction, but they're negative. And I can do whatever I want to do with this. Plus 36x minus 4, right? My end behavior is still going to be the same. It's going to be in the same direction one way or the other, right? Now, let's say I have a fourth term, right? So x to the fourth minus that, right? What do we think is going to happen? My largest function is still even, or my largest power is still even, so my end behavior is going to go in the same direction. Similarly, if I look at x cubed, right, and I zoom in a little bit, oh, I'm way up there, aren't I? Right, so my x cubed behavior is odd, which means that the two are going to be in opposite directions as we go toward x equals infinity and -infinity. And that's really all the odds and the evens are. And so if I look at the different functions, tangent is going to be an odd function, right? Because they go in different directions. Cotangent, also an odd function, whereas secant and cosecant are even functions because the asymptotes head in the same direction. All right, I think that covers most of your homework. I hope you enjoyed this, and remember, if you need anything, email a homework problem or a question, and hopefully I'll make another homework helper video. And if you want to find out more about me and my tutoring, go to rockpiletutors.com. Have a great evening.